Our last rotational topic is going to be angular momentum. And since we're talking about momentum, we know that we're talking about a conserved quantity. So let's go ahead and start with what we're comfortable with, and that's translational motion. For translational motion, momentum is given by the symbol rho, and rho equals mass times velocity. If we replace the linear quantities with rotational quantities, then we can get the angular momentum. For angular momentum, we use the symbol L. And L equals, we replace mass with moment of inertia, and we replace linear velocity with rotational velocity. And so here, rotational momentum equals moment of inertia times rotational velocity. And it's a perfectly analogous equation. So let's go ahead and let's remember, if we can, for Newton's second law, we were able to show Newton's second law in terms of change in momentum. And that was actually a more holistic approach to Newton's second law because that accounted for objects that changed mass. So here, Newton's second law is written as the net force is directly proportional to mass times the acceleration of an object, and this is for linear objects. We can replace the net force, we can replace acceleration with change in velocity over change in time. And then we would get mass times change in velocity over change in time. And we know that mass times change in velocity, that's Vf minus Vi. And if I distribute the m, it would be mVf minus mVi. And that would be the momentum at the end minus the momentum initially, which would be, in fact, change in momentum. So that means that the net force is directly proportional to the change in momentum over time. And this is also where we get our impulse momentum equation. Well, we can do the exact same thing for Newton's second law for rotational values. And remember, we showed that Newton's second law for rotational values is given as the net torque is equal to the moment of inertia times rotational acceleration. So again, I'm going to replace the value rotational acceleration, this time with rotational change in velocity over time. And if I get the final rotational motion minus the initial rotational motion, and I distribute my moment of inertia, then that would be final rotational momentum minus initial rotational momentum, which would be the change in rotational or angular momentum over time. And so you can see that this is a directly analogous relationship here, and that is going to work for each situation. And we also know that since we can calculate the relationship between an applied force and the rate of change of a momentum, we know that according to the laws of physics, that this is a conserved quantity. And if it's a conserved quantity, then we know that when the net external torque on an object, and in this case we can say any net torque on an object, if it's equal to 0, then we can have angular momentum as a conserved quantity. And that is analogous to, we say that momentum is conserved when there is no net external force acting. And so same physical concept. And that gives us the law of conservation of angular momentum, which states that the total angular momentum of a rotating object remains constant, conserved quantity, as long as the net torque on that object is 0. So that's saying that at any instant in time, the rotational momentum, the angular momentum, which is given by moment of inertia times angular velocity, will be equal to the product of the initial angular moment of inertia times the initial angular velocity. That'll always be constant. And here I could have said this equals this, and that's a constant. And we know, in fact, that that's true, but I'll put it into the terms of moment of inertia times angular velocity, because when it comes to rotating objects, it's actually very true that the moment of inertia for most objects is just as likely to change as the angular velocity. So that means that the moment of inertia can change for objects when their speed changes. There's a lot of interesting phenomena that happen in terms of changing the moment of inertia and looking at what the effect of angular momentum is. So the first one that we're going to consider is a skater. And a skater with her arms stretched out is going to spin with an angular velocity of omega. And what we know here is because her arms are stretched out, that means her particles for her fingers, which all have mass, are actually a very large radius away from her axis of rotation. So that means that when we calculate her moment of inertia with her arms outstretched, her moment of inertia is going to be large because more of her mass is further away from her axis of rotation. So that means that initially, if she has a large moment of inertia, she may have whatever her small rotational velocity is. But if she brings her hands in close to her body and her axis of rotation still hasn't changed, then that means that now the sum of the mass of all of her particles times the radius distributed from the axis of rotation, her moment of inertia, is much smaller because the radius there is much smaller. And that means if the initial has to equal the rotational momentum at any point in time, since that's constant, if the moment of inertia goes down, then in order to compensate, the rotational velocity must increase. And so this is how, without applying any net torque, an ice skater can speed up her rotation just by bringing her arms in closer to her body. And likewise, this can be done by a diver. Divers start with a long shape, and that means that if she's going to, in this case, actually rotate this way, then that means that her axis of rotation would be through her body like that. Now, when she's stretched out, much of her mass is at a far radius from her body. But if she curls up, what she's doing is she's bringing her mass closer to her axis of rotation. And as she does that, her moment of inertia is going to decrease. And as her moment of inertia decreases, in order to conserve angular momentum, her velocity, her angular velocity, is going to have to increase. And as a result, her body begins to rotate. And this is why divers will spin in a couple of circles before they're realigned with the water as they want to be, and they stretch their body out, reduce their rotational velocity until it's almost non-existent, and then they're able to dive in the water. One of the things that we want to keep in mind in this situation is that the net torque on this situation is equal to 0 because nothing here is applying a force to her body in a way that would cause a torque. However, the net force does not equal 0 because if she's in free fall, then that means that all along the way, gravity is acting on her body the whole time. So that net force is not 0, even though the net torque is 0. And that's okay because gravity acts at the center of mass. So when a force acts at the center of mass, the net force will not necessarily be equal to 0, but the net torque will equal 0, and that's because the radius equals 0. And so that means that angular momentum can be conserved even when the net force on an object is not 0, just so long as the net torque on that object is 0. So let's take a look at what type of application, what type of problems can we consider for this. The first one that we're going to take a look at is a conceptual. We're going to take a look at a figure skater's momentum and kinetic energy. So when a figure skater speeds up by bringing her arms in, does her kinetic energy also increase? Well, we know that angular momentum equals moment of inertia times rotational velocity. And so now we know that when she brings her arms in, her moment of inertia is going to go down and her rotational velocity is going to increase. So that means that you get a decrease in I and an increase in rotational speed. And that has to be proportionate, right? So if you have I naught omega naught, that's got to equal, if you decrease the moment of inertia by half, that means that you have to increase the angular velocity of 2. So you're going to have twice the angular velocity when you have half the rotational inertia. And so you know it's a direct relationship. The product has to be conserved. So that means let's go ahead and let's run with this. Kinetic energy is given by 1/2 I omega squared. So that means initially it would equal 1/2 I omega squared. Afterward, the kinetic energy would have to equal 1/2, and then we have 1/2 the initial rotational moment of inertia, and then we have twice the rotational velocity. And that's not a direct relationship, that's a squared relationship. So while this equals 1/2 I omega squared, this is going to equal 1/2 and 1/2 is 1/4, and 4/4 is I omega squared by comparison. So we can see that we did increase our kinetic energy for rotational motion when she brought her arms in. And so that begs the question, where the heck did this energy come from? Remember that the amount of work will change the kinetic energy. So that means that something must have done work on her and on her system to cause that increase in kinetic energy. And we know it wasn't an external torque. So that means that it had to be some internal work. And so it turns out that the amount of kinetic energy that caused her to increase her kinetic energy came from the work that she did on her arms to bring them in near her body, and that was positive work done to increase her kinetic energy. And if she brought her arms back out again, she would be doing negative work or work against the system, which would decrease her kinetic energy. Let's go ahead and let's take a look at a situation that's a little bit more numerical and see what kind of problem solving we can do with rotational or angular momentum. So we're going to be looking at a small mass, and we are not given a mass value, so we're going to designate that mass M, and it's attached to a string that revolves in a circle on a frictionless tabletop. So if there's no friction, then we know that the net torque is going to be equal to 0. Now, the other end of the string is passing through a hole, and it's initially given a spin or a speed of 2.4 meters per second as it rotates around in the circle. But that circle has a radius of 0.8 meters. If the hand pulls down until the radius is 0.48 meters, pardon my typo, then we want to know if it's a frictionless surface, so the net torque is 0, what's that final velocity going to be? So we can actually use the conservation of angular momentum to solve this problem. We know that L1 equals L2, so the initial moment of inertia times the rotational velocity will equal the final moment of inertia times the final velocity. And since this one object is a one-point object, we can say that for each value, the moment of inertia is going to be equal to mr squared. Since it's one-point object, we can treat it like a point-like mass. So rewriting that, we get mr1 squared omega 1 equals mr2 squared omega 2, and right away we can see, oh thank goodness, I don't have a mass value, I don't need a mass value, so my relationship is r1 squared omega 1 equals r2 squared omega 2. And I'm given a linear velocity, so I know my relationship is v equals r omega. So omega is going to equal v over r, and I'm going to go ahead and I'm going to replace that into the equation. And it's going to be r1 squared times v1 over r1 equals r2 squared v2 over r2. And I am quickly going to simplify my equation, and I get r1 v1 equals r2 v2. Solving for v2, v2 equals r1 over r2 times v1. So it's a ratio, it's a fraction of the initial value. The initial value is 2.4 meters per second times the ratio of 0.8 over 0.48 meters. That is going to give me a value of 4.0 meters per second. So I can check conceptually. The radius decreased, so that means the moment of inertia decreased. Therefore, the rotational velocity and the overall velocity should have increased. The linear velocity increased, and that makes sense because that linear velocity should have increased by the proportions that I searched. And so this is actually pretty straightforward, simple problem solving that we can do with conservation. Now we're going to look at estimation. The last type of problem solving is a star collapse. And when you study astronomy, you get to learn about a bunch of interesting interstellar bodies, and one of my favorites is the product of a supernova. And I'm not talking about black holes, I'm talking about neutron stars. Neutron stars generally tend to come from very large stars that collapse, and as they collapse, all of their mass is brought in until it's spinning very quickly. And these neutron stars actually emit a form of energy, because remember, they have kinetic energy, and that kinetic energy can be transformed in space. And so we often can pick up radio electromagnetic radiation from a neutron star, and if we do that, we know that a neutron star is there, and we can determine approximately, given that data and given the frequency of data that we collect, what the speed and size of those neutron stars are. So we're going to predict how fast a neutron star would rotate if it initially started out with a mass twice the mass of our sun. So the mass of this neutron star is going to be 2 times the mass of our sun. And we have that value if we decide that we need to plug it in, but I'm going to hold off in case I can skip that step. The initial radius of the neutron star was 7 times 10 to the 5th kilometers. And once the neutron star collapses, generally neutron stars collapse until they're about 6 miles across or 10 kilometers across. Initially, the star had an angular rotation of 1 revolution every 10 days. And we're going to notice here that this angular rotation is given in revolution per days. That is not a correct unit, and so we're going to need to be careful when we plug that in, that we make sure that we plug in 4 correct units. But we know that this is going to be a conservation of angular momentum problem because there's no net torque. There's no force getting applied to the star that causes it to collapse. There's a gravity that causes it to collapse, but gravity acts at the center of mass, so there's no net torque. So we can say that the initial moment of inertia times the angular motion of the star will equal the final moment of inertia times the rotational velocity of the star. And we can generally assume that stars are spheres, so we're going to say that the star had a moment of inertia of 2/5 mr squared, because that's the moment of inertia for a spherical object. So I'm going to go ahead and I'm going to plug that in. 2/5 mr1 squared times omega 1 equals 2/5 mr2 squared times omega 2, and immediately I'm going to gratefully clean up this equation. And I was right. I didn't have to actually plug in that mass value for our sun. So now I get the relationship of R1 squared over R2 squared times omega 1 will give me omega 2. And I didn't replace these with linear values because I have rotational values. So go ahead and plug that in. And I need to change this 1 revolution per day. That's actually per day. If I change days to seconds, that's a frequency. And I know that I have an equation, frequency equals omega divided by 2 pi. So I can actually replace my omega 2 with a frequency. The frequency in revolution per days, which is what I want, would be given by omega 2 over 2 pi, which would be given by R1 squared over R2 squared, and then I'd have omega 1 over 2 pi. So since this is a frequency, if I change this to seconds, and then I can plug directly in omega 1 over 2 pi is frequency, so F2 equals omega 2 over 2 pi equals R1 squared over R2 squared times the frequency of object 1. So plugging that in so I can get revolutions per second, I get 7 times 10 to the 5th kilometers, and that's going to be squared, divided by 10 kilometers, and that's going to be squared. And I didn't change from kilometers because it's a ratio, so the unit, as long as it matches, doesn't matter. And then I have 1 revolution occurring every 10 days. 10 days can be converted with 24 hours per day times 3,600 seconds per hour. And if I do that calculation, I end up getting 6 times 10 to the 3rd revolutions per second. So when a star collapses from a massive size down to 6 miles across, its rotation increases rapidly. It was doing 1 revolution every 10 days. Now it's doing 6,000 revolutions every single second. And that, kind of in short, gives us our conservation of angular momentum. Remember that these values have direction, and we can determine direction using the right-hand rule, where our fingers represent the direction of rotation. So if something is sideways and it's spinning up and around, then that means that its direction would be forward. If something is in a plane and it's rotating clockwise, then our thumb would point down, so that means that our direction would be down. And that's going to be for all vector quantities. That's going to be for angular speed, angular acceleration, angular momentum. Everything that we can use is going to follow the right-hand rule for direction.